Order, order, order! The time for submitting evidence is over. We need to make a decision. I ask the engineering students of the jury to please go and deliberate on who made the better case. Did Tresca make the better case for his criterion, or did von Mises make the better case? Please go and deliberate, and while you do, try example 3 and maybe try to apply both theories on your own and see which one maybe makes more sense or is the best theory to criterion to apply for engineering failure. I know by now that you are good at drawing Mohr's circle for 3D states of stress, and I hope you will be able to apply Tresca and von Mises' criteria to check whether or not you're expecting failure to have occurred for this particular element with the stresses shown. I've labeled these stresses. Sigma x is 28 ksi tension, sigma y 4 ksi tension, tau xy negative 16 ksi. Sigma z is 0. I plot my Mohr's circle for the xy plane that is shown here. I follow the same steps I followed always for Mohr's circle. This blue circle then represents all the possible states of stress in the xy plane. I want to solve for the radius, so I'll sketch in an orange triangle as such. I see the base is 12, the height is 16, so this is a 12, 16, 20 triangle or a 3, 4, 5 triangle. So I can see that my radius is going to be 20 ksi. I could also verify this doing calculations. Once I know my radius, I can solve for sigma 1 and sigma 3, and I also know that sigma 2 is equal to 0. I'll zoom in here to get my inner circles sketched. It's less important that we know exactly the values on these circles, but for completeness sake, I like to have the 3 circles sketched for my Mohr's circle for 3D states of stress. Once I have my 3 circles, I can easily tell that the absolute maximum shear stress will occur on the blue circle, which is going to be equal to the radius, which is 20 ksi. I can solve for my principal stresses. Sigma 1 is the center plus the radius, so that's going to be 16 plus 20, which gives me 36 ksi. Sigma 2 is 0. Sigma 3 is 16 minus 20 ksi, which is a negative 4 ksi. Now that I've identified my principal stresses and my absolute maximum shear stress, I can go ahead and check Tresca and von Mises' failure criterion. So for Tresca, it says that failure occurs when the absolute max shear stress exceeds a certain value, which is Fy over 2, a critical value. So that means the radius, 20 ksi, is that greater than our yield strength, 50 ksi divided by 2? So is 20 greater than 25? No. Therefore, we do not expect failure to occur based on the Tresca criterion. For von Mises, failure occurs when the maximum distortional energy exceeds a critical value. And in formula terms, it says failure occurs when... I'll go ahead and just write it down and you can copy it into your notes. Plugging in the values for the principal stresses, I can go ahead and do my calculations. Is 1456 greater than or equal to 2500? Or I like to take the square root of both sides. Is 38.16 greater than 50? No. So based on the von Mises failure criterion, we are not expecting our design to fail. I hope this made sense, and I am looking forward to hearing your verdict. I hope you found that example enlightening. I would say based on my experience, I see that both criteria can be used to safely design engineering materials. Especially if we consider the biaxial stress case, both of the failure envelopes were very close to one another. In fact, von Mises just gives a little bit extra, and if we look at the test data is all over the place. So, I think we can't apply either of these criterion straight out, that we probably would want to include some sort of factor of safety, and when we do, both of them will give pretty accurate approximations of failure. I do see one key advantage, though. One key advantage to von Mises, when we look at that failure envelope, is that von Mises, the equation creates an oval. And so an oval is a continuous function versus Tresca, which kind of made that hexagon, and that is not quite a continuous function. When you're applying these criteria, especially in computer programs, it's easier to check failure versus a continuous function, and even in 3 dimensions, a continuous surface, versus Tresca's criterion, which is kind of a piecewise function, and you would have to do a bunch of less than or greater than checks in the computer code, which ultimately takes a little bit more time. But otherwise, both criterion work, in my opinion. However, it's now time to hear from the jury. Jury, do you have a verdict?
Yes, Honor, we do.
And what did you find?
We, the engineering students of mechanics and materials of the jury, find in favor of